Ever wondered what it would be like to take a peek inside Einstein's brain?
Well, get ready for a wild ride, because today we're diving deep into the mind-blowing world of Albert Einstein,
Okay, maybe not literally inside his brain, but
but as close as we can get.
exactly. We're cracking open his revolutionary 1905 paper on the electrodynamics of moving bodies.
The one that introduced the world to the mind-bending concepts of special relativity.
This is the paper that changed everything, folks. It redefined our very understanding of space and time.
And we're here to break it down for you piece by fascinating piece.
Now, I know you're thinking diving into a physics paper doesn't exactly sound like a barrel of laughs.
But trust us on this one. Einstein had a knack for posing deceptively simple questions that would unravel the very fabric of classical physics.
Yeah, he was kind of like a physics rock star, you know? He knew how to grab your attention and make you question everything you thought you knew about the universe.
Absolutely. And this paper is a prime example. Right from the get-go, he throws down a challenge with this seemingly simple question.
It's all about a magnet and a conductor, right? Something about them moving relative to each other.
Right. He asks, and this is where it gets really interesting, should it matter which one is moving?
It's like one of those brain teaser riddles, like what happens when an unstoppable force meets an immovable object?
Exactly.
Yeah.
And that seemingly simple question poked a giant hole in our everyday understanding of physics. We tend to think of motion as being relative, right? But when it comes to electricity and magnetism, the classical view suggests that it should matter which object is moving.
Okay, so let's say you have a magnet and a wire moving past each other.
Right.
You'd think the effects would be the same whether the magnet or the wire is the one in motion, right?
You'd think so. That's certainly the intuition. But classical physics, as it stood, suggested otherwise. And Einstein, he saw this inconsistency as a clue, a hint that something much deeper was going on.
And that's where his two postulates of special relativity come in.
Two deceptively simple statements that would turn the world of physics on its head.
Seriously, these postulates are like the foundation for so much of modern physics.
Absolutely. The first one states the laws of physics are the same for all observers in uniform motion.
Okay, so break that down for me. What does that actually mean?
It means no matter where you are or how fast you're moving, whether you're on a bullet train or floating in space, the same fundamental laws of physics apply.
So it's like the universe doesn't play favorites.
Precisely. And that leads us to the second postulate, the one that truly bends the mind. The speed of light in a vacuum is constant for all inertial observers, regardless of the source's motion. Let that sink in for a moment.
Okay, I'm trying to wrap my head around that one. It means even if I'm in a spaceship flying at like 99% the speed of light, and I turn on a flashlight, the light beam will still travel away from me at the speed of light.
Exactly.
Whoa.
It seems counterintuitive, I know. In our everyday experience, we're used to speeds adding up. You walk on a moving train, you add your speed to the train speed. But light doesn't play by those rules. It's the ultimate speed limit, a cosmic constant.
So the speed of light is constant. That's a tough one to swallow, but what does that actually mean for our understanding of, time and space?
That's where things get really wild. This simple-sounding postulate has some seriously mind-bending consequences. It means our everyday notions of absolute time and space, those ideas that everyone measures those things the same way, well, they just don't hold up.
You're saying time and space aren't as straightforward as we always thought?
Not even close. Einstein showed that time and space are intertwined or relative.
Yeah.
They depend on your frame of reference, It's like looking through a funhouse mirror. What you see depends on where you're standing.
Okay, so where does Einstein take this in the paper? How does he explain it?
He uses this really clever example, something we can all wrap our heads around, a train arriving at a station at 7 o'clock.
Okay, I've been on a train. I've seen the clock. What's so special about that?
Well, he points out that the train pulling up and your watch saying it's 7 o'clock, they might seem like perfectly simultaneous events, totally in sync.
Yeah, seems pretty straightforward.
But that's only true from your perspective, standing there on the platform.
Well, someone else might see those events differently. How?
Picture another observer on a different platform, but this one's moving past you, really fast, like a bullet train. For them, those same two events, the train arriving and your watch hitting 7, they wouldn't happen at the same time.
Wait, really?
Their perception of now would be totally different from yours.
So just the act of moving at a different speed changes how you experience time itself.
You got it. Time isn't this universal thing ticking away at the same rate for everyone. It's more like a river, flowing at different speeds depending on where you are and how fast you're moving.
Okay, my brain is officially starting to hurt, but how did Einstein actually prove this?
He came up with this elegant thought experiment using, get this, synchronized clocks and light beams. Imagine two clocks, perfectly in sync, one on a moving train and one on the platform.
Okay, I'm with you so far.
Now, picture a beam of light bouncing back and forth between mirrors, one at each end of the train car.
Like a high-speed game of cosmic ping pong.
Exactly. Now, here's where it gets really wild. Because the speed of light is constant for everyone, right? The observer on the platform sees that light beam traveling a longer distance than the observer on the train.
How is that even possible? It's the same beam of light.
That's the whole point. The train is moving while the light's traveling, so the path the light takes, at least as the person on the platform sees it, is longer. And since the speed of light can't change, the only way to make sense of that is if time itself is passing differently for each observer.
So the faster you move, the slower time goes for you.
You got it.
Yeah.
It's called time dilation. For the person on that train, time is actually passing slower relative to the person on the platform.
That is absolutely wild. Okay, but we're not done with Einstein's paper yet, are we? There's more, right? Like length contraction?
You're on a roll.
Mm-hmm.
And the best way to understand length contraction is with that rigid sphere Einstein talks about. When it's just hanging out, it looks perfectly spherical, right?
Oh, makes sense to me.
But now, imagine that same sphere, but it's flying through space at like half the speed of light.
Okay, got it. So what happens? It turns into a football.
Well, to someone watching it zip by, it wouldn't look spherical anymore. It appears squished, like compressed in the direction it's moving.
Wait, so it's not just time that's relative. Space itself is changing based on how fast you're moving. It's not an optical illusion or something.
You got it. It's not really shrinking. It's more like the very fabric of space and time is getting distorted by how fast it's moving. And that is length contraction. Of course, we don't see this stuff in everyday life because we're not moving anywhere near the speed of light.
So reality itself is kind of subjective based on how fast you're moving.
In a way, yeah. It's all connected. And this leads us to probably the most famous consequence of Einstein's theory, right? Time dilation and the twin paradox.
Okay, yeah. The twin paradox, everyone's heard of it. One twin blasts off in a spaceship. They age slower. But how does that actually work?
Picture it. Two identical twins. One stays here on Earth, living their best life, while the other one, they hop in a spaceship and zoom off at a good chunk of the speed of light.
Okay, I'm picturing it. So what happens next?
Well, because that spaceship twin is moving so incredibly fast, time slows down for them relative to their Earthbound sibling.
Wait, so you're saying when that space twin finally makes it back home, they'll have aged less than the twin who stayed on Earth?
Exactly. It's like a one-way ticket to the future.
Wow. Time travel is real.
Well, not exactly time travel like in the movies, but in a way, yeah. By messing with your velocity and getting close to the speed of light, you could theoretically experience time passing slower relative to someone back on Earth.
That's mind-blowing.
It really is. And it's a direct consequence of how Einstein revolutionized our understanding of velocity. Remember how we normally think about speeds adding up? Like if you throw a ball in a moving train, it seems like the speeds just add together from, say, a stationary observer's point of view.
Right, that's like physics 101.
Yeah.
But Einstein found a problem with that, right?
Exactly. Well, in our everyday world, those speeds are way too slow for it to really matter. But when we start talking about velocities that get close to the speed of light, well, things get a little weird. Einstein showed that you can't just add velocities together like we normally do. There's a cosmic speed limit.
Right. The speed of light, that ultimate barrier.
Exactly. So let's say you're in a spaceship cruising along at, say, 90% the speed of light, and you fire a missile forward at, 20% the speed of light.
Okay, I'm picturing it. So to someone watching, that missile would be going 110% the speed of light. Right.
That's what you'd think. But nope, not how it works.
So what happens? Does it just, stop dead in its tracks?
Not quite. Those velocities, they combine, but they do it according to this special formula Einstein came up with. It's a formula that basically guarantees that nothing can ever go faster than the speed of light.
Hold on. There's an actual equation for this.
There is.
Yeah.
It's a bit much to get into right now, but the main takeaway is that the final speed of the missile, as seen by our observer, would be insanely close to the speed of light, but it would never actually hit it, let alone go faster.
Wild, huh? That is wild. So even though the spaceship is already going super fast and the missile's even faster, the speed of light is still this unbreakable barrier.
Exactly. And as mind-blowing as that is, it's been proven right over and over in experiments. And the implications for physics, huge. And speaking of light, it's not just time and space that are affected by motion. Remember, Einstein's paper, it also digs into how all this affects our understanding of light itself. Stuff like the Doppler effect.
Okay, the Doppler effect, I know that one from sound, right? Like
Right.
when an ambulance siren goes by, it's higher pitched coming toward you and then lower pitched as it moves away, that classic wee sound.
You got it. And Einstein showed that light waves, they behave in a similar way. Remember how we talked about motion messing with how time passes? Well, it's the same deal for light waves. If a light source is moving towards you, those light waves get kind of squished together, leading to a higher frequency.
And frequency is what determines color, right? So would that light look bluer?
Exactly. It's called blue shift. And on the flip side, if the light source is moving away, those waves stretch out, the frequency drops, and the light shifts toward the red end of the spectrum redshift.
It's like the universe is saying, hey, I'm moving over here.
That's a great way to think about it. And this isn't just theoretical stuff. Astronomers use redshift to study the expansion of the universe.
Oh, right. By looking at how redshifted the light from distant galaxies is, they can figure out how fast those galaxies are moving away from us, right?
Exactly. It's one of the biggest pieces of evidence we have supporting the Big Bang. And it all traces back to Einstein's incredible insights into light and motion.
It's mind-blowing to think that one paper from over a century ago could have such a massive impact. We started with magnets and conductors, and now we're talking about time travel, warped space, the expanding universe, all thanks to Einstein.
It really speaks to the power of curiosity, of questioning what we think we know. Einstein wasn't afraid to challenge the status quo, to look at the universe in a whole new light.
And in doing so, he unlocked some of the universe's most incredible secrets. So what mysteries are still out there? What other groundbreaking discoveries are just waiting for someone to ask the right questions, to challenge those old assumptions? We might need a new Einstein.
Or maybe, just maybe, that next Einstein is listening right now, inspired to unravel the next layer of the universe's mysteries.
This deep dive has been an incredible journey through the mind of Albert Einstein and his revolutionary theory of special relativity. If this conversation has your brain buzzing, we encourage you to check out the full text of his paper. We've got a link for you in the show notes. And until next time, keep those minds open and never stop questioning.